And with that, maybe we can go to the third speaker for the session, who is Joern Bannies. And he will, from UBC, and he will tell us about doping-induced topological phase transition in the nodal-line semimetal platinum antimony telluride.
Yes, thanks for the introduction. Exactly like Ming said, I'm going to be talking about lanthanum antimony telluride and the most recent results we obtained on the topological phase transitions in this material. I would like to first acknowledge the people involved in this work. So this has been like a very strong collaboration with people in the group of Andrea Damascelli, namely Matteo Micciardi and Sean Kung. And also, very importantly, all the data that, or most of the data that I'm going to be showing in terms of the ARPIS work was acquired at the QMSC beamline at the Canadian Light Source. As an outline, I'll first give a short introduction into square-net materials because, to square-net materials so that we all have the same starting ground to understand when we look into the actual materials, which are a tetragonal phase of lanthanum antimony telluride, as well as an orthorhombic phase. And then lastly, I'm going to be talking about surface doping and how we can convert these phases in situ. To begin with, most of the interest that has been come up in the past few years in square-net materials can be understood based on a very simple model. So we just take a simple two-dimensional square net, as we have here on the left-hand side, and we choose the unit cell here such that it is non-primitive, because that is the unit cell how it will occur in most real-world materials. So in order to get the model that we're about to develop as close as possible to real materials, we choose this unit cell. Then if we put any main group element, for instance, antimony, then we can derive a band structure based on realistic hopping parameters, and the band structure looks like the one shown in the middle, where we have an S block well separated from the P bands. Now, the main feature I would like to point you to are two band crossings. The first one is between Px and Py along gamma m, about halfway here. And those bands have another crossing right at the X point. And these two crossings are special in the sense that they're enforced by the non-symmorphic symmetry in the square net. In the square net, we have an n-glide plane, which is a mirror operation followed by a translation along the diagonal of a unit cell, and it's this symmetry operation that dictates these crossings to appear. To get closer to real materials, we need to fill this with electrons, and here the filling of interest is 6 electrons per side, as is found, for instance, in zirconium silicon sulfide. As you can see now, the Fermi level is cutting directly through these two band crossings. And in terms of the Fermi surface, we have one single Fermi surface sheet, as shown here on the right, which has this characteristic diamond shaped. And if we take the two things together, the fact that we know halfway along gamma m, the Px and Py bands are degenerate, and right at the X point, together with the fact that there's just this one single Fermi surface sheet, we can conclude that along this entire sheet, the two bands are degenerate, and therefore they form a so-called nodal line, or in this case, because the nodal line has a closed shape, we can call this a nodal loop. And this nodal loop is an interesting feature in terms of its topological properties, because it carries a non-trivial Barry phase inside, and that gives rise to a number of different features. The other thing you may notice about this Fermi surface is that it's highly nested. So here I'm just showing one of many possible Q vectors that nest the Fermi surface. And therefore, just in this very simple model, this square net is very prone to either perform a structural distortion to gap out these Fermi surface parts, or develop charge instability. So this really sets us up with an interesting problem or set of properties, because on the one hand, we have this topological non-trivial feature of a nodal loop, but that is close to being unstable. So that really allows, if we can find a material where we can break certain symmetries, we can study how the topology evolves as a consequence of symmetry breaking. Now, this was just the simplest possible model. In the real world, we need to put this into a 3D lattice. And one of the materials where we can realize this is zirconium silicon sulfide. Here we have a silicon occupying the square net, and those silicon layers are sandwiched in between double layered slabs of zirconium and sulfur. The DFT calculated band structure looks like this, and the most important part to look at is the gamma m direction, the diagonal of the Brion zone, because here we can see this red band and the black band that are very steep and almost linear over quite a big energy range. And importantly, they also cross just slightly below the Fermi level. And this is directly a consequence of having this square net feature in real space. So this really shows the direct relation here between a crystallographic feature and the electronic structure in K-space. This material is stable, unlike what I've said before with the nested Fermi surface, because there's hybridization with the zirconium D states. You can see the zirconium just sits a bit above the silicon planes, and therefore the hybridization is quite strong. And this makes this material stable. So that is all nice, but it's not really suitable for what we are aiming to do, which is breaking the symmetries. Luckily for us, we can also put a different set of elements, for instance, rare earth cations, antimony, and tellurium. In this case now, antimony is occupying the square net position, and then the rare earth and the tellurium are forming these double slabs. And otherwise, the crystal structure is left completely unchanged. But the key difference now is by replacing zirconium with a rare earth element, which is mostly in something like a 3+ oxidation state. The key difference is that we now don't have d electrons anymore to stabilize the square net feature. And as a consequence, different distorted structures are realized. For example, if we look into the cerium, antimony, tellurium system, what the first thing to know is we have the option to tune the composition in a very wide range, basically all the way from x equals 0 to x equals 2. And as you can see in this phase diagram, where the lattice parameters are shown as a function of antimony content, you can see that close to the ideal 1-to-1 composition in terms of antimony and tellurium, we realize this tetragonal structure that is shown on the left-hand side. But if we go away from this composition towards the antimony deficient side, which is electron doped, then orthorhombic structures are formed and complicated superstructures can be formed, charge density waves with even multiple Q vectors can be formed. And this directly shows that in these systems, we can realize different structures just by, if you wish to call it, internal doping. And so this presents an ideal playground to exactly study what happens as a function of symmetry breaking. Specifically in lanthanum antimony telluride, we're looking at the tetragonal phase, which you've seen already now, and one of the orthorhombic phases that is shown here on the right-hand side. And the first thing you may notice here is that the c-axis is doubled compared to the tetragonal phase, but other than that, the crystal structure is very similar. We still have these antimony layers with a bit of distortion. I will discuss that in a second. And then we have these lanthanum and tellurium kind of double layer slabs. In terms of the distortion, that is the main difference between these two materials. So for the tetragonal phase, we have these ideal square nets, and most importantly, there is an n-glide symmetry translating this atom along the diagonal of the unit cell. In the orthorhombic phase, on the other hand, because now we distort the square net into zigzag chains, because the bond length intra and inter chain is now different, there's no longer an n-glide symmetry. And that will turn out to be the crucial difference between these two phases. The other thing to note here is that even though we form these zigzag chains, the difference in the bond length between intra and interchain is still not very much. So at the end of the day, these chains do not behave as isolated zigzag chains, but more as a plane of chains, so that we're not close to any one-dimensional physics here. So first we need to grow these materials. And it turns out that when we grow crystals from vapor transport, we usually obtain tellurium-doped crystals, for instance, with a doping of about 10%. And if we do a powder XRD measurement, we can see that there's one single 200 peak, and that really shows this phase is indeed tetragonal when we have this tellurium-rich composition. However, if we choose a different method, namely if we grow the crystals from antimony flux, what we find is in the powder pattern that this one single peak that we previously had splits into two peaks, the 200 and the 020 peak. And this clearly demonstrates that we have a distortion into an orthorhombic structure. If we take some data from the literature, we can construct a similar phase diagram as we've seen for the cerium before, where we plot the lattice parameters as a function of the composition. And as you can see, there's a very narrow range, a bit on the tellurium-rich or antimony deficient side, where we can realize this tetragonal structure. And then on both sides of this tetragonal regime, we realize orthorhombic structures. And that is really a unique situation, because what we are trying to do exactly is we change the internal composition as one way to induce doping. So we study crystals in this regime here and in the tetragonal phase. But what we can also do is we can dope the surface of these materials in the experiments, as I will show you later. So this is a unique situation because it allows within the same material to study all these different symmetry breakings. As I said, the key difference between the two phases, the tetragonal and the orthorhombic phase, is the presence or absence of the n-glide plane. And to understand the consequence of this presence, we constructed a very simple tight binding model with the unit cell shown here. We put only px and py orbitals, 2 electrons per side, which corresponds to 6 electrons per side in the real material, and we take lattice parameters from the experiments. Then the band structure along the gamma M path looks like this, and we have this gapless band crossing here about halfway between gamma M, and that sits right at the Fermi level. The first step now to distort the structure is to make A and B lattice parameters different, as I'm showing here, obviously exaggerated. There's a few small changes happening, but most importantly, this band crossing here is still gapless. So that shows we need to take some more step to introduce a gap opening. Only if we move this center atom out of the center in the unit cell, which then causes the breaking of the n-glide symmetry, only if we do that, there's a gap opening in this nodal-line feature, and that gap is indeed of massive size. So we're talking about almost 700 millielectron volts. And if you put that in relation to the small change in the actual crystal structure, this is a huge energy scale. So with this simple model, we get an idea of what might happen in the real materials. And to understand those, I would first like to discuss the DFT calculated band structures, first here on the tetragonal phase. What you see here is on the top fat band representation. And again, it's instructive to look at the direction gamma M. Here you can see these blue bands that are linear over, again, a considerable energy range, or and are crossing just below the Fermi level. And these states are derived from antimony, px, and py. And this again shows, even in this material, the square net feature is defining for the electronic structure near the Fermi level. And these antimony-derived bands, they also form this characteristic diamond-shaped Fermi surface sheet that we had seen already in the very simple model. Now, because this is a real material, we also have some other bands here, and namely, we have this electron hole pocket near the gamma plane, and this has a three-dimensional shape, as opposed to the diamond shape electron pocket, which has negligible out-of-plane dispersion. In terms of the orthorhombic material, there's not much difference in the band structure overall, but again, with one key difference, and that we can see along gamma S, which is now the diagonal of the Brillouin zone. You see again these blue bands with quite high Fermi velocity, but now there's a gap developing here. And that is on a similar order of magnitude as what we had seen in the tight binding model. So we're again talking about roughly 600 millielectron volt. And this gap opening can also be seen in terms of the Fermi surface, because now we gap out most of these previous diamond-shaped, most of parts of that Fermi surface get gapped out. And those remainders of the electron pocket, they still have the a negligible out-of-plane dispersion. So this really shows that we still keep this kind of two-dimensional characteristic. So with this, we can confirm that, at least based on a theory side, our very simple model that we use, time binding model that we used, is able to capture the essential physics of symmetry breaking in the real materials, the tetragonal and the orthorhombic phase. To probe this experimentally, we employ ARPAS measurements, and namely the data here that I'm showing, as I said, were acquired at the Canadian Light Source. So for the tetragonal phase, the Fermi surface looks like this here in the upper left panel, and that will remind you of the diamond-shaped Fermi surface that we have seen before, with the difference now that we see two concentric features with the same shape, and that is because we're now in the bulk electron-doped sample, so the band crossing lies below the Fermi level. But if we account for that band shift in the DFT calculations, we can get a very nice agreement. For this tetragonal phase, we obviously, as a starting point, need to establish that this is really a gapless nodal-line semimetal. And the easiest direction to see that is the gamma M direction again. When we use linear horizontal polarization, we see there are these steep linear dispersing bands, and there's no sign of any gap. So that's already a good sign. But we're missing a second branch here to form a band crossing. And
sorry, can I interrupt? Do you mind?
Oh yeah, of course.
Yeah, where's nodal line in the data?
That's what I'm getting to.
Oh, sorry, thank you.
So here we have a very strong matrix element, such that when we use horizontal polarization, we only see the inwards dispersing branch of this Dirac cone, if you want. While if we change to linear vertical polarization, we see these outwards dispersing branch on top of a lot of noise background. So if you stitch these two images together, you again arrive at what the theory predicts, that is this gapless crossing here. And the only reason there is a small gap here is because of the finite sampling in the K mesh. We can also confirm this by fitting momentum distribution curves. So if we fit rows in this data, and we do this for both polarizations, we obtain the positions of these bands as a function of energy, and we can confirm, yes, indeed, these two bands are crossing and there's no gap. So with that, we have established the starting point, or in the parent phase, the tetragonal parent phase of this material. Now for the orthorhombic sample, the Fermi surface looked quite different. We see that now we no longer have fourfold symmetry anymore because we're in the orthorhombic phase. And these electron pockets here at the edge of the Brillouin zone are in very good agreement with what we can calculate based on DFT. So that's already a clear sign of a big change in the electronic structure. But now if we look again at the diagonal of the Brillouin zone, which is gamma S now, we see that these bands, which were formerly gapless here, develop an enormous gap. So you can see that the valence band tops out at around 400 millielectron volts. So what we can see, say, based on this data, is that the nodal line develops a gap of at least 400 millielectron volts. We're limited to that because in our case, we cannot easily probe the unoccupied state. So that's we can only give this lower bound. But that really shows the experimental verification of all the theoretical considerations we have performed before. To give you a direct comparison, here on the left-hand side, again, we have the tetragonal phase, which we obtain in the electron-doped regime, where we have linearly dispersing bands with no gap. While if we go onto the slightly hole-doped regime, we observe this massive gap developing in those linear band crossings. Now, these energy scales are similar enough that we can do a little trick in the experiment. And if we start here from the orthorhombic phase, again, you see this is a different sample, but again, we have this gap on the order of 400 millielectron volts. In the UHV chamber, we can in situ electron dope the surface of the material by depositing potassium. What simply happens is the potassium adsorbs on the surface and mostly gives away its electrons. So thereby the first few layers of the crystals get electron doped. And if we do this on a very short time scale, we open this shutter, we do this procedure for 30 seconds, you can already see a clear change in the band structure where this faint conduction band is coming down now, so the gap is shrinking. If we repeat this step multiple times, you can see now the features even becoming more clear. And if we repeat this step a few times, we eventually arrive at a situation where we again see linear bands with no sign of a gap. So it appears that based on just depositing potassium on the surface and electron doping, the first few layers, we can change the topology back into what we had observed for the bulk tetragonal phase. You can see this also in terms of the Fermi surface. So again, here we start from the pristine Fermi surface with only two-fold symmetry, and then clearly after the potassium doping, we have restored four-fold symmetry, which is yet another hint that now at the surface, we have restored tetragonal symmetry as a consequence of electron doping. And we can compare this with the bulk tetragonal phase. So when we took different crystals that were grown in the electron-rich regime, and you can see the clear resemblance between both the spectra and the Fermi surfaces. So with this, it really seems that the energy scales here are small enough in terms of relative between the lattice distortion and the gain in electronic energy through the distortion. These energy scales are very similar, and even small changes, for instance, and bulk doping just by roughly 10%, or by doing pure electron doping, if you wish, through potassium deposition, we can tweak the balance between these energy scales. What's even more interesting is, in terms of this in situ doping, this process is even reversible. So here I just like to quickly flash this. Again, we start from a pristine orthorhombic sample where we have a gap in these linear bands. We potassium dope the sample all the way into the regime where we observe linear bands with no band gap. And if we then take an additional step, and now we try to desorb the potassium, so we kind of take back the electron doping, we again arrive at a state that is similar to the original pristine state where the gap developed. There's a bit of intensity here that we don't know the origin of yet, and the quality of the spectra gets worse because the treatment is quite harsh on the surface, but you can still clearly see how we revert back to this original band structure. In summary, we found that if we electron dope lanthanum antimony telluride, we obtain a tetragonal phase, and this tetragonal phase features a gapless nodal line. However, if we go into the slightly hole doped regime, the sample is orthorhombic, and those nodal lines get gapped out as a consequence of the breaking of n-glide symmetry. So this system really presents, again, a unique opportunity where we can both achieve this doping and changing the topology as a function of small changes in the bulk doping, but even more if you want a more pure version of electron doping through the surface doping that I've presented you in the last few slides. With this, I would like to thank you for your attention, and I'm open to take questions.
Thank you so much, Joern. This is really fascinating. While we wait for questions, can I ask that one?
Of course.
May I ask? So, I'm trying to think about how you can change the orthothrombicity on the surface. Are you thinking about this gap phase as really due to some sort of electronic-driven phase rather than lattice-driven phase? Like, because, yeah.
Yes, well, at least our interpretation of this is really electronically driven to gap out these highly nested Fermi surfaces. And then if you want, the lattice kind of follows this transition, because it seems that really those energy scales are very, very similar to each other. And then small changes can just tip it over into either way.
Can I ask, if you put in the actual observed orthothrombicity, how much of a gap do you get in comparison to your measurement?
So from the experiment, we're limited to whatever we see between Fermi level and the top of the valence band. So this is 400 millielectron volts. Mm-hmm. In terms of the theory, between the tight binding model and the DFT, they're in very good agreement. They both give about 600-700 millielectron volts gap. Unfortunately, we can't really prove that with STM. The idea, well, usually you would try to maybe see the conduction band through potassium doping, but it turns out that this simultaneously does this transition. So we cannot really access this through ARPIS.
I see. So you're saying, like, with the orthothrombicity, you already have a really large energy scale for your gap.
Yes.
Interesting. Thank you. I see Shiming have your hand up. Shiming, do you want to ask your question?
Thank you, Ming. Thank you for your nice time, Joern. Yeah, the transition or the change of the Fermi surface from this kind of orthorontic shape to the diamond shape, I think that's dramatic. I have one question because I previously did the ARPIS on the gadolinium antimony telluride series before, and of course, at that time we also noticed, there is a difference between tunability from tetragonal phase to orthorhombic phase. And when we did the ARPIS, one thing we noticed that actually caused some difficulties, and there is a twinning effect. When you go to if you go polarized optical microscopy, you check the crystal, you will find that there is more twinning. It's really hard for us to get the really nice clean this kind of valley, like in your right top image, you can see like you only get a residue from one kind of the valley instead of the other. Do you get the detwinning process, or actually, you happen get one such kind of single domain area than you did at ARPIS?
That's a good point. So
yeah, from here you can see there's definitely twinning.
So this image here is taken with polarized light, and you can clearly see the twinning. So we did not detwin the crystals. Based on, I had a look at these crystals, and I chose the ones where I saw like big enough domains or big enough twins that we could probe them with the spot size that we have at CLS. So we're talking about on the order of 20 by 150 micron. And just by scanning the sample, we were admittedly lucky enough to find a region where we just probe a single twin.
Oh, I see.
For other measurements, it would of course be helpful to detwin the crystals, but we haven't really looked into that yet.
Oh, I see. So the ARPIS is actually on this composition, which is antimony rich instead of antimony deficient.
Yes.
Okay. Yeah, got you. Yeah, thanks.
Any other questions? Timil has a question.
I have a question, but please cut me off if the time's running out. Yeah, exciting results. So if one wants to be greedy, is there a way to probe the surface states?
So there's some surface states there that we see when we, now where is it? It's not really obvious from the Fermi surface, and I don't have the cuts here that show this, but right at the X point, there's a surface state there that we can probe with the ARPIS. It's just that we do not focus on that. So all these bands that I'm showing here, they're representative for the bulk. There is, like I said, there is a relatively prominent surface state that you could see if you took this cut here, but so far we have only looked into the change in the bands that are representative for the bulk.
But there's supposed to be topological surface states, so I don't know whether that potentially can be resolved.
So that is a good point. The situation is a bit more complicated than the simple model here, because we have different nodal lines in the case z equals 0 and the case z equals pi plane. And those Berry phases that has been shown for other materials, those Berry phases, they cancel out each other. So you may only get a very small momentum region where you would observe this surface state. And it turns out in this material here that region is just so small that we cannot really probe it with the resolution we have in the ARPIS experiment.
Okay, thank you.
Thank you. And I guess, thank you, Joern. Again, this is a very beautiful result.